I'm going to go through these problems in part because we will be using regressions later on, a bit of econometrics in the course. So let me be sure that you are comfortable with at least the basics. Okay, so let's look at problem number 3 on the midterm. I'll make this a bit easier for you to see it by increasing the font size. In this case, we have an actual model for cash demand in Kazakhstan that will test the inventory model. So there is the equation for Kazakhstan from 2000 to 2013, and it includes uh, independent variables that also appear in the theory of money as inventory. Let's take a look at how we can test the theory. Okay, so as you have pointed out, the theory predicts a coefficient on the natural log of income of 0.5 and a coefficient of minus 0.5 on the natural log of the interest rate. And as though there is no intercept in the model. So let's take a look at how to determine whether or not the actual coefficients in Kazakhstan are close enough to the predicted values as to justify or accepting the theory. So now I'm going to go to the whiteboard to talk a bit about econometrics. So the idea is that we don't have all information about every possible state of the universe. So we have to use a sample to test the inventory theory. Just a few observations from Kazakhstan, in this case, of about a dozen observations. So given the possibility that the sample may differ slightly from general circumstances, how can we be sure that we can put our confidence in the estimates that come from the sample? So here's the idea. We theorize that in the real world, the elasticity of cash demand with respect to income is 0.5. So as you point out, a 1% increase in income is predicted to increase cash demand by 0.5%. So how do we test this claim? With a sample. The basic idea is that if we take enough samples, the coefficient estimate in most of them should be pretty close to 0.5. So if indeed in the real world, this is Jean, can you hear me? So if this model indeed describes the real world, then in a typical sample, you should observe a coefficient close to 0.5, maybe not exactly 0.5, but close enough for jazz. So here's what we will do. We will assume that the model is right. And then we will compare the sample estimate of the coefficient to the predicted value. If the two figures are close enough, then we will basically accept or not reject the inventory model of cash demand. On the other hand, if they are very different, then we will reject the inventory model. That's the basic idea. Okay, so far. So in the graph, here's what we will do. We argue that under general circumstances, the elasticity of cash demand is 0.5, but may vary a bit from 0.5 from one sample to another. So maybe for 2000 to 2010, we have an estimate of 0.6. For 2010 to 2020, maybe it is 0.4. But in other case, it should be pretty close to 0.5. Okay, so here is, sorry about my shaky artistry. Here is the distribution for the coefficient in cash demand. If the model is correct, then the average value of this distribution should be about 0.5. Right there. The vertical axis in this case is measuring the probability of observing the given value. So, for example, if the height here is 40%, then we may anticipate an estimate of 0.5 40% of the time in 40% of the samples. All right, so if we are close to that coefficient, we will accept the inventory model. But what happens if, in fact, the coefficient is way out yonder? For example, here, here is a value that is nowhere close to 0.5. Of course, it's 1.5. Or another example, here is a value that is negative, maybe minus 2.5. So what do we do if in our sample we have an extreme estimate like 1.5 or minus 2.5? Well, the distribution suggests that we are very unlikely to observe a value that is this extreme or even more extreme if in fact the correct value is 0.5. If the two figures are that different, then we will reject the inventory model because it is not likely that given a value in the real world of 0.5, we would actually observe one of these extreme values. Okay, so far. Okay, good. One possibility is to simply uh, compare the coefficient estimate to the sample estimate, but instead, uh, economists usually refer to a statistic that is representative of the coefficient estimate called T. The T statistic is equal to the sample estimate minus the uh, predicted estimate. Divided by a measure of dispersion in sample estimates called the standard error of the coefficient estimate. So I hope that makes it easier to see. So if T is large in absolute value, then it suggests that our sample estimate is very different from our prediction of 0.5 in this case. There is more of a divergence than we really anticipated because of normal dispersion in sample values. So I'm going to note this here. If T is large in magnitude, then it suggests that our sample estimate differs a lot from our prediction. A given normal dispersion in some estimates across samples. The dispersion is measured here in the denominator of the t-statistics. So here's an example. Suppose that we get on the income coefficient in the sample of a value of, let's say, 5. So there is our sample estimate. Our predicted estimate from the inventory model is 0.5. And then let's say that our standard error in this case is equal to 1. Then our t-statistic is 4.5, which turns out to be very large. We will see this later on. So given the large t-statistic, we should reject the inventory model because it does not predict well what we observe in our sample. All right so far. Again, pardon my clumsy orchestra, but here is a distribution of the t-statistic. Now notice that if the model is correct, t should have a value that is close to 0. The sample estimate is very close to the predicted estimate. So if the inventory model is right, we would expect to see a t-value that is close to 0. Now, suppose instead that we observe a t-value of 2. Or another possibility, -2. In that case, the observed value differs so much from 0 that we would have to reject the inventory model because we are very unlikely to observe a value of 2 or greater in magnitude if the inventory model is correct. In fact, it turns out that there is only a 5% chance that we would observe a value that extreme if the inventory model describes the real world. So here is the rule of thumb. If t exceeds 2 in absolute value, then reject the model that is represented by our hypothesis, in this case, a de-inventory model. Otherwise, if t is less than 2 in magnitude, basically accept the inventory model, at least not reject it. And then there you have it. Are you comfortable with the intuition behind the t-test? We assume that the model is correct, calculate the value of t. If the model is correct, would be 0, and then take a look at the sample to see whether or not the value that we observed is close to 0. It's that simple. Okay, so back to the actual model because experiment. The coefficient on the natural log of an income is 3.6. The inventory model predicts that the coefficient is 0.5. And then the standard error, the income coefficient is 0.1. So that is in the denominator of the t-statistic. So in this case, the t-statistic is 31. So what should we do? Should we accept the inventory model or reject it?
Reject it?
Yeah, good. 3.6 differs a lot from 0.5, exactly. Especially given that there is not much dispersion expected in the coefficient across samples. So the success that we should reject the inventory model, that is relative to income. Now, what about the interest rate? That observed coefficient is 0.4. But from the inventory model, we had anticipated minus 0.5. So here's the numerator of the t-statistic, minus 0.4, which we observed, minus the predicted value, which is minus 0.5. And compare that to the expected dispersion in coefficient estimates because of random samples of 0.1. Now, what do we do? Do we reject the model with respect to the interest rate? or accept it.
Accepted.
Yeah, good. Or not rejected, that's good. Why? Plus you move.
Because it's less than 2.
Imagine this. So it is pretty close to the predicted value. Minus zero point 0.4 is just in the neighborhood of minus zero point 0.5. So this time you get a result that is consistent with the inventory model.
Is it when we accepting or rejecting it, the inventory model, do we always range the answer between -2 and 2?
Oh, that's a good question. No, yes and no. Yes, in the sense that most econometric studies adopt a magnitude of 2 for t as the boundary on the estimate that we should be getting if the hypothesis was correct. But no, in the sense that there is no particular reason why we should use 2 rather than 3 or 1.5. It all depends on how conservative we want to be about testing the hypothesis. So to see this, let me go back to the whiteboard for a second. Okay. It turns out that if the model is correct, the inventory model in this case, then there is only a probability of 5% that we would observe a value of t in magnitude that is bigger than 2. In other words, here or over here. That region in there. So I will note that up here. Usually, we reject the hypothesis if the probability of observing what we do observe, the central value, would be less than 5%. If the hypothesis was correct. However, basically, your son is asking why 5%? Why not 10%? Why not 1%? And there is no good answer to that question. 5% has become the traditional level of significance. That was, I mean, we would tolerate an error of only 5% by adopting that is by rejecting the hypothesis. But in reality, it all depends on how important the hypothesis is to you. So if we want to keep the hypothesis unless there is a very, very good reason to reject it, then maybe we will adopt a level of significance that is smaller than 5%, maybe 1%, something like that. So in reality, the level of significance that you would adopt is up to you. Some statistical studies suggest that we should permit a, a level of significance that is as large as 20% because the theory suggests that we should adopt certain variables that we are testing for. Okay, so far. So does it take care of your question about the probability of rejection when the hypothesis is correct? In most cases, truth is probably a reasonable border because it suggests that the difference of the sample estimate from the predicted value is twice as large as standard dispersion in coefficient estimates. Maybe two is okay. Okay, now here's one last question. What is the predicted intercept in this model? If the model is correct, what will our intercept be? Well, where's the intercept? There is no intercept predicted by the inventory model. So now we can test the hypothesis that the intercept is zero. In our model for Kazakhstan, the intercept is minus 21, which is nowhere near zero. So it is very easy to reject the hypothesis for the intercept. And so there you have it. Mixed results for the inventory model in Kazakhstan. However, we don't have a lot of data in this sample, only 14 years of data. These are annual estimates. So one problem is that we may not be able to measure the coefficient very precisely just don't have enough data to do that. Well, if that is the case, then we will have a lot of dispersion and estimates of false samples. And therefore, the t-statistic will be small because dispersion increases the denominator of the t-value. More data would help. But if you're interested in testing the model itself, you will find the data at the National Bank at its website, interest rate and income. If you would love some extra credit, you can try answering question number one by next week. The last question that I really make sure that you're comfortable with is about adaptive expectations. So let's take a look at what this equation is saying. The idea behind the model is that people will adjust their estimates gradually, only gradually, uh, as their information changes about the price level. Here is our expectation of the price level PT based on information that we had last year. So if it is 2019, we estimate what we think the price level will be, and this is our expectation for 2020. The model says that our expectation of the price level is equal to our previous expectation plus an adjustment for the error that we made last time. So uh, this expectation of the price level at time t minus 1 be formulated at time t minus 2. So these expectations occur 1 year ahead. And then finally, here is the actual price level last year compared to our expectation. If it turned out to be wrong last year, then we will adjust our expectation for this year. So, for example, suppose that in 2018 we had anticipated a very low price level, no inflation. But in reality, the price level last year turned out to be very high. In that case, we realized that we had underestimated the price in the past, and therefore we will raise our expectation of the price next year. We think that we may underestimate otherwise the price level. We take our past errors into account. So A is positive, usually understood to be between 0 and 1. Are you okay with the intuition? Well, we are using past information and then we will adjust gradually. Okay, so let's look at part B. suppose that the price level at time t minus 1 equals our expectation. In other words, suppose that we are correct about last year's price level. What then will we expect for next year in the price level? Let's see, if last year we were 100% correct about the price level, then this bracketed term will equal 0. So what now is an expectation of the price level at time t. Curiously enough, it would be equal to our expectation of last year's price. So in other words, if we were correct last year, we will think that we will be correct this year as well. And finally, one more exercise for you. Suppose that the price level, the actual price last year is 100, when we had expected it to be 90. So we underestimate the price. And suppose that A is equal to 0.5 in this case, then what is the expected price level for time t from the model? So what do you think? Using this formula, let's see, our error about last year's price level is 10. A, the adjustment factor is 0.5. So this says that we will add 5 units to our expectation of the price at time t. Last year, our expectation had been 90, and we now know that that is an underestimate. So we say, okay, let's raise our expectation for the price this year, but let's fence just a little bit. Let's raise the expectation not by 10 units, but instead by only 5 units. So there is a very gradual adjustment to our mistakes in the past. What do you think of the model? Adapted expectations.
What is the thing written x in the brackets t minus 1? Because in here you ask what is the expectation of pt, right?
On the left-hand side, exactly, yes.
What's the next expression x to the in the brackets t minus 1?
Oh, that's a very good question. The vertical line here indicates that we are given information that we will use in the expectation. In this case, the information that we are given is old information. the form of expectation of the price at time t by using information that was true at time t minus 1. So this is a backward-looking model. We're not using uh, information about the future, but instead information about the past. In particular, we use the actual price observed at time t minus 1. We have that information, and then we will base our expectation of the price next year on what we now observe in the prior year. Some economists suggest that this is not a very realistic model. Surely people will use all the information available to them, past, present, or predictions about the future perhaps. They're not using just actual information about the previous year. Okay, other questions about expectations. Okay, good. Let me take a moment to discuss with you why expectations may matter. So, for example, the National Bank of Kazakhstan each year surveys consumers about their expectations of the price level in the coming year. Keynesian economists suggest that there is a relationship between the inflation rate and the unemployment rate. A negative relationship if we're using logs in these cases. This is called the Phillips curve. Are you familiar with this term? Maybe we talked about it when we looked at the business cycle. The idea is that there is a trade-off that we can make between higher prices and higher employment. If we are willing to live with a high rate of inflation, then we can reduce unemployment. So, for example, here is Kazakhstan that has a long run rate of unemployment of about 4%. And here is our average inflation rate of about 7%. The Phillips model says that if we are willing to live with a higher rate of inflation, let's just say 10%, then they can reduce the rate of unemployment, maybe in this case, to 2%. So it's wonderful. The national bank can manage the national economy just by targeting a rate of inflation if the model is correct. But in reality, at least in the West, it turns out that we don't have this nice negative relationship between unemployment and inflation. Instead, the relationship is very messy. Look something like that. The problem is to try to explain why this trade-off between inflation and unemployment may quickly break down so that the Phillips curve is no longer valid. One possibility suggested by Milton Friedman in his article The Role of Monetary Policy is that people adjust to place expectations very slowly due to adaptive expectations model. So when prices suddenly rise, producers tend to think that this signals rising demand for their products. That's right. If you find that at your hotel, your rivals are able to raise their room rates, you will say, good, people are going back on vacation. I will raise my hotel rates as well. So thinking that trends are good, they hire new workers. And thus unemployment goes down. So there is the relationship between the actual rate of inflation and the unemployment rate. Unemployment falls because people make a mistake about the price. However, eventually producers realize that they were wrong about the perceived increase in consumer demand. Prices are rising not because of higher demand, but because of inflation. So once they figure that out, they will lay off their recently hired workers. Producers cut back. and unemployment rises in that case. So maybe for a while, maybe for a year, we do observe a fall in unemployment, but then producers are cutting back because they realize that it is inflation that has increased and not consumer demand. So now we are moving in this direction. That's the intuition behind the reality that the Phillips curve sort of looks like that. They have a long run vertical value.
But sometimes this line, this graph is right. So, for example, if you think about the producer of, I don't know, a wheat, for example, and their customers are from different countries. And when you have inflation, for example, you sell for an export, you sell in dollars, for example, you get higher. No, for example, you sell in your own currency, and your wheat becomes cheaper for customers from different countries because you had an inflation, and you get more customers of it, more production, and there could be jobs, for example, needing workers to get this production to be going. Like you will have bigger production, and you creating new jobs and stuff like that.
No, but go ahead.
Could this not be possible?
Yes, it's a very interesting point. That maybe we are observing an indirect relationship, not a direct one, between inflation and the unemployment rate.
Mm.
So you're suggesting, I think, that if we have, for example, devaluation of the tenge, then we can sell more wheat to the United States since the dollar is buying more tenge than before. And then as a byproduct, the devaluation will raise prices in Kazakhstan. Yes, I think that's correct. But it is not described a direct relationship between inflation and unemployment. Instead, the inflation in your story is a byproduct of tenge devaluation.
Okay, yeah.
It's perfectly possible. No, it's a very good point. Okay. Other questions, comments? If you're looking for a paper to write, it would be very interesting to estimate the Phillips curve from Central Asia to Kazakhstan. I have not seen that done yet.